Hello, welcome back to Chapter 9, Section 4, where we are going to be talking about a physics application of quadratic functions and how the transformations of quadratic functions actually mean something when we deal with how things move. Physics is just basically, it's really complicated, but physics is basically the study of how things move. And since everything is moving, then physics is really the study of everything, in a way. And I'm sure that if I was sitting here with Sheldon from the Big Bang Theory, he would probably both agree with me and correct me. So I don't know if you guys watch Big Bang Theory. But we're going to keep it kind of simple because probably most students don't take physics until their 11th grade. So probably you haven't had physics yet. Every now and then I get a student in algebra, intermediate algebra, who is in physics, so it's not always that way. Okay. So all we're going to do in this problem is we're just going to drop things, and just to make it fun, we're talking about dropping water balloons. Now, when this dude right here lets go of his red water balloon, he just lets go of it. He doesn't throw it up, he doesn't throw it down. That's important. He just lets go of it. If he throws it up, like tosses it upwards a little bit, that's going to change things. And if he just totally like shoves it down, throws it down, like he sees somebody he really doesn't like down here and he just throws it at him, that's going to change things too. What we're going to be talking about with both of these people, whatever their names are, I don't know who they are, they're just going to let it go. They're just going to let go of it, and it's going to fall all on its own. What's affecting the water balloon? Well, the person who's letting it go is no longer affecting it. It's in what we call free fall. And the only thing affecting free fall is gravity. So, the height, I'm going to write it up here, the height of an object that's in free fall at time t, because we're going to measure this in seconds. We're going to count how many seconds it takes, like until it hits the ground, or even until it just drops like a couple of feet. This is 64 feet, this is 144 feet. They should probably not be dropping water balloons from like that height. They're going to hurt someone. This is equal to negative 1/2 g t to the second power plus initial velocity times t plus the initial height. Now, before you panic about that, a lot of this you don't need to know. This part right here, if v is positive, the initial velocity is positive, then that means you're going to be like throwing the water balloon toward the sky. And if it's negative, that means you're throwing it down toward the ground. A moment ago I just said we're not throwing it at all, we're just dropping it. So this is actually going to equal 0, which is nice. We're going to ignore that. This part right here, that comes from the fact that you're on Earth. G is the constant. It's not a variable. It's the constant that refers to the gravity of the planet or moon that you're on. Since obviously, well, maybe it's not obvious, I don't know. But we're just going to assume that these people are on Earth. In feet, since we're in feet per second squared, the constant of gravity, gravitational constant I should say, is about 32 feet per second squared. So we want half of 32. By the way, this negative 1/2, the negative tells me that it's going to be pulling everything down. The 1/2 actually comes from calculus, and if it's okay, I'd kind of like to just say everyone just go with it for now. So, what do we know? Well, this is going to be 0, and the negative 1/2 times 32 is going to be negative 16. So, my height at time t is actually going to be negative 16 times t to the second power plus 0. But notice I've left out this initial height. Those little subscript zeros means the velocity at time 0 and the height at time 0. We call it naught, like h naught. All right. This is how high above the ground, and wherever you define the ground is up to you. Okay. You probably learned about relative motion and relative points of reference in middle school science. Okay, I know my kid is learning that, like right now while I'm recording that. So wherever that is, in this case, it's going to be the ground, and the ground where this building is. So it's 64 feet above the ground. So this would be h equals 0. All right. So this is going to be a parameter. It's not a variable, and it's going to be different for this function and different for that function. So we're going to say that's very similar to the c that we just talked about. So for this guy, whatever, I don't know, can't even tell. It's hard to tell, it's a cartoon. This person, that height is going to be negative 16 t to the second power plus 64. Now for this person, that height is going to be negative 16 t to the second power, and it's always going to be negative 16 if you're talking about feet. It's going to be different if we talk about meters, because a meter is longer than a foot. Okay, but this is always going to be the same as long as we're talking about things on Earth. For the second person, it's going to be plus 144. So those are my two height functions. Okay, I replaced the c with 64 from here, and I replaced it with 144 for here. Now we're going to graph it, and you're going to use Desmos to graph it. And when you use Desmos to graph it, you're going to have to change and mess with the scale a little bit. I've already messed with, and how do you do that? You hit here where it says wrench, and I adjusted a little bit, but I went from my x from -1 to about 5, and if I need more than that, I can change it. And from my y-axis, I went from like about -20 or so. Like I said, after I typed it in, I changed it a little bit. And I went to like about 200 to start, and then I zoomed in a little bit more. So you can start with the boundaries from like the smallest x to the largest x and the smallest y to the largest y, and then adjust it by pinching it afterwards. Okay? Here's my first graph. This is the person who drops water balloon 64 feet high. Okay. Now there's a couple things to notice about here. First of all, Desmos does not know that this is a real problem. Okay? Desmos is just graphing negative 16x squared plus 64. So I end up with like an entire quadratic function here. But that actually doesn't make sense. Because, and again, I'm using x because Desmos knows what x is. You are smart. You know that that's actually time, t for time. Okay? We always try to use variables that represent what we're studying. That's why I used t here, but Desmos doesn't know what t is. Whoops, went upside down on me. Okay. All right. So I'm gonna do one thing. Just gotta make sure I can find where it's at. I'm always, yeah, there it is. I always do this on my keyboard, actually. So sometimes it's hard for me to find stuff. X is greater than or equal to 0. All right. Now, what did that just do? It means that I started right here at time 0. There's no such thing as negative time. So I'm going to change that to x equals 0. And this does not mean that it could, maybe the person threw it sideways or something, but this is just a graph of time. Okay? The water balloon probably dropped straight down. Probably. There's nothing in the story that says otherwise. Okay? This graph is not the path that it took. It could, but it doesn't have to be. This is just the graph of time. So to go from 64 feet down here to 0, it took 2 seconds. And of course, there's nothing beyond this either, so I should probably try to eliminate that part of the graph too. All right, maybe I think I can do that. Say y is greater than or equal to 0. Yeah, cool. So it just showed that part of the graph. Why did it not go beyond? Because once it got to the ground, the water balloon stopped. It burst. Okay, now let's look at the other graph. Oops. Let's zoom out a little bit to see what's happening. Again, I've got negative time here, and I've got height less than 0. So let's change that up a little bit. And if you can ignore it without having to change it, that's perfectly okay. I'm just showing you how to do it if it really bugs you. All right. So we do x is greater than or equal to 0, and whoa, sorry, I hit the x. I'm sorry, I got to start all over again. Y equals negative 16 x squared plus 144. X is greater than or equal to 0. Whoops. Ugh, I did it again. I'm so sorry. Hang on. Y equals negative 16 x squared plus 144. I'll make sure I don't hit the x next time. So x is greater than or equal to 0. Stop. Okay, now I'm going to do this. Haha. And then I also want y to be positive. Okay. I bet you that was fun to watch, I'm sure. All right, so now this does not mean that the other person threw the water balloon further. All right, this is just a graph of time versus height. So at time 0, when the person dropped the water balloon, it was 144 feet above the ground. And as you go, I'll try to do it this way. As you go, the x represents the time in seconds. So here's about 1 second. Now it's 120, probably about 128. There it is. Almost. I can barely get it. About 128 feet above the ground. After 2 seconds, about right here, it's about 78 feet above the ground. After 3 seconds, now it's at 0. So because of the extra 144 feet, it took an extra second. Now this is really kind of cool. So if I show this too, 64 to 144, that's more than 2 times higher. All right, double 64 is 128. So this is even higher than that. But it only took a second longer for it to hit the ground. That's because when you drop things, gravity accelerates. Gravity accelerates the speed, okay? And if there was no air resistance, oh my gosh, I'm getting into physics. If there's no air resistance, then they would continue following at this path. Eventually, the air starts to push back. That's how parachutes work. All right, we'll see you in the guided practice problems.